5.4. Happy day, we're there. The definite integral. Okay, we're going to start with a beautiful new piece of notation. We're going to talk about signed areas rather than the areas we usually talk about, and we're going to talk about properties of this thing, and we'll do an example. Okay? All right. Okay, this is all the stuff I keep saying over and over again. Last time, we were trying to find the area under a continuous, non-negative curve over a certain closed interval. And what did we do? Again, we chopped this up into subintervals. Over each, we built a rectangle, such that the rectangle rose to the level of the function. We found the areas of the rectangles, and we added them up. And that gives you an approximation called a Riemann sum of the area under the curve. And as you take the limit, increase the number of rectangles, narrow each one, okay, so that each one more closely approximates the area of the slice. Then we get the true area in the limit under the curve. And that's given by that expression there. All of that is from Leibniz. Okay? Okay. This sort of structure is fantastically important, and I'll show you some examples next time of other places where it's important. It's so important it has its own name and has its own symbol. Okay, so look at that thing in the bottom right, and now look at this. Okay. This guy on the right-hand side, okay, this thing defines the definite integral. This stuff on the right-hand side is exactly what we had last time, except we now have x sub I star. X sub I also works. The reason we said x sub I star is to acknowledge that it doesn't matter where you sample. Okay? In the limit, it shouldn't matter where you sample for a dignified function. Okay? So, we're doing what we did before. Increase the number of rectangles, sum over all the rectangles. This is the width of a rectangle. This is the height of a rectangle. Exactly what we had before. The width of each rectangle, exactly what we had before. The positions of the endpoints, as we had before. And in this case, we're just acknowledging that you can sample anywhere on a subinterval. It doesn't have to be right endpoint, it doesn't have to be left endpoint. Anywhere on the subinterval should give you the same answer. Okay? Your answer should not depend on where you sample. Okay? So this gorgeous thing is called the definite integral, and that's how it's defined. Okay? The integral from a to b of f of x dx, or with respect to x, is defined as that. Okay, again, remember what we were talking about was the area under the curve. Okay? So that's essentially what that is. You don't need to know the following. Incidentally, you don't actually have to partition into equal size subintervals. You can do it to unequal size subintervals, provided in the limit you make them all go down to nothing. Okay? But in this class, we only talk about regular subintervals. Okay? A regular partition where all the subintervals are the same size. Okay. Here we go. A, B, f of x, dx. Okay. This lovely thing is called the integral sign. These are called the limits of integration. This is the lower limit of integration. This is the upper limit of integration. Not really that kind of limit, okay? The function you are integrating, okay? The thing you're graphing and trying to get the area under is called the integrand. This guy is an old friend. We've seen this before. It's called a differential. Or an infinitesimal. The variable this guy indicates is the variable of integration. Okay, the differential tells us what our variable of integration is. So So you may remember the dy dx notation, that dx on the bottom tells you where you're differentiating with respect to. This guy tells you what you're integrating with respect to. Okay, and again, whenever we have elegant notation, it's usually Leibniz who's responsible for it. Okay. So incidentally, anyone who's seen the Stewart textbook for calculus, I'm willing to bet my arm that the reason that's always on the cover is because the F hole on a violin looks like that. Okay. Nargle check. All right. All good? Okay. If this thing exists, if that limit exists and it doesn't depend on the sample points, whatever, so if this thing exists, we say f is integrable or integrable on that interval between a and b. Okay, like differentiable. Now you can take the integral, you say it's integrable or integrable, one or the other. Okay? All continuous functions are. Okay, so on any interval, if you're continuous, you're integrable. I gotta learn how to pronounce it, I'm gonna say it 100 times. You're integrable on that interval. Okay? You can take the integral on that interval. Okay, and that was proved by our friend Riemann. Good? Okay, so you've got a nice friendly continuous function, you're going to be able to calculate this thing. Okay, if you have finitely many jump or removable discontinuities, that's fine. Okay, so if you're continuous on the interval, you're good. If you're continuous almost everywhere, but some places you've got jump or removable discontinuities, that's cool too. Okay, and if you want to picture a graph like that, and you can see that you can calculate areas with a graph like that, so everything's cool. Calculating this guy, so evaluating this, is called integration. Grammar is important, isn't it? That's almost good. Okay? We have the integral. Calculating is called integration, and if you can calculate it, you say you're integrable on the interval. Incidentally, again, Riemann proved this business, and one of the most important open questions in math right now is something that Riemann said might be true. Big, big, big open problem, called the Riemann hypothesis. Surprised you don't need to know that. Okay, last class, what did we show? So last class, what did we show? We said that the area from 0 to 1 under the parabola x squared is 1/3. Okay, so we can now write this in this lovely way. Okay, from 0 to 1, we integrate x squared with respect to x, and we get 1/3. Okay? All right. Okay, let's look at this again and admire this again. In the limit, we're doing something smoother than we do with this sum. Okay? So instead of adding up the areas of rectangles, this is going to be somewhat sloppy, okay? Instead of adding up the areas of rectangles with some finite width delta x or some non-zero width delta x, we now essentially are looking at rectangles that are impossibly thin. Okay, so you can think of that as impossibly thin. Okay, so instead of delta x, we talk about dx. Instead of sampling to get the areas of those rectangles at points x sub I star indexed by I from 1 through n, we now sort of sample everywhere. Okay, so we sample at all x. Okay, instead of adding up a finite number of rectangle areas, okay, as we did over here, we're going through all x, okay, and we're adding up the sums, okay, we're essentially adding up the areas of those impossibly thin rectangles on a continuum. Okay, so as we go from here to here, we're doing something more smooth. Okay, so instead of the Greek capital letter S, we're using this long, smooth, lovely S. Okay, the notation is somewhat suggestive. Okay, so this should all make sense. You're getting the area from A to B. Your functions in terms of x, and that's that. Okay, does that make sense? Again, as you take the limit, everything becomes smoother, your notation changes. Okay. So that's a number, okay? So given a particular function, f, and particular values, of A and B, this guy is a number. Okay, don't go thinking it's a function of x, okay? It's a number. Okay? Like that guy was. Representing something like an area. Okay. The variable of integration. Look, you learn math through examples, okay? So as you do stuff, notice that the stuff I'm saying makes sense. The variable integration lives in the integral. It's a dummy variable. Okay, the variable integration being this x here. Okay? So what am I talking about? No. We've seen things like this before, okay? When you write things like this, it doesn't matter what you call this index, okay? You're going to get the same answer. And no matter what you call the index, you're still here talking about the sum of the integers. Oh boy, the sum of the squares of the integers from 1 through 5, okay? So the sum of the squares of the first 5 positive integers. And that's always going to be the same. It doesn't matter what you call the guy if you use your index. Okay, so you can think of that as a dummy variable. It lives inside the operation, and nobody outside sees it. Okay? Same deal here. Okay, as you take the limit as x approaches 1 of this thing, okay, it doesn't matter if you call that thing y instead or z instead, you're always going to get the same answer. Okay? Doesn't matter what you call it, it lives inside the operation. Exactly the same deal here. Okay? And I think colors have disappeared as usual for some reason. Okay? Pretend that was red, pretend that was blue, pretend that was purple. So again, it doesn't matter what you call this guy, it's a dummy variable, it lives inside the integral. Outside, we don't talk about it. Okay? So outside of this, we don't talk about x. Outside of this, we don't talk about x. It just spits out a value, independent of what you call this thing. and that's that. Does that make sense? Okay, it lives inside the integral. Okay. Signed area. Okay, so last class we talked about getting the area under the graph of a function that's continuous and non-negative over the interval. Okay? So what if the function's not continuous? What if the function's not non-negative? Or in other words, what if the function is sometimes negative over the interval? Okay, so again, when we have something non-negative, we live up there, and so we can talk about the area under the curve, and that's equivalent to that kind of thing. So what if you're not always above the x-axis? Okay, so in that case you get something that's not quite an area, but it's a reasonable extension of the area. Okay, so what if you do something like this? Okay. As you build the Riemann sum and you build your rectangles, what do you get? You get something like that as one of your rectangles, let's say. Okay? That contributes to your Riemann sum, your approximation of the area. It contributes an amount equal to the negative of that area. Okay? So when you multiply the value of the function by that width, you're going to get a negative thing there, so you're going to add the negative of that area. Okay? So in the limit, as you increase the number of rectangles, when the function dips below the axis, you contribute a negative amount to the integral. Okay? So, in general, a definite integral doesn't necessarily tell you sign, it doesn't necessarily tell you area, it tells you the signed or net area. Okay? Which is loosely speaking the area above the x-axis minus the area below the x-axis. Okay, so what am I talking about? So suppose you got something that looks like this. Okay, where the function's positive, we're still contributing area, okay? So the definite integral tells you the sum of the areas upstairs, okay? So again, like before, the area under the curve when you're upstairs, and when you're downstairs, you subtract that area. Does that make sense? It's exactly what you'd expect, okay? So it's all the area enclosed above minus all the area enclosed below the axis. Yes, ma'am?
So to fix that, can you just effectively take the absolute value of the function?
No. Yeah, so okay, good. No. Suppose that area was 1, that area was 2, that area was 1. You go 1 minus 2 plus 1. Does that make sense? It's what you'd expect, right? So this makes a negative contribution. You don't go minus the negative. You see what I'm saying? So you're not going minus a negative, you're going minus a positive. So if you think of areas as positive things, then that's what I'm talking about. Does that make sense? Yeah. Yeah. So it's possible for stuff to cancel. Yeah? Okay. Again, there's nothing unreasonable going on here. It's exactly what you'd want to happen.
Net area.
Okay. Okay. Nice way to think about about this, again, this is part of the reason we talked this velocity stuff. Okay, so if this was a velocity time curve, as you're up here, your velocity is positive. You're going forward. 1 second. You're increasing your accumulated displacement. Okay? If your velocity is negative, you're going backward. You're decreasing your accumulated displacement. Okay? So that jives with this. Okay? So as you go under here, you're taking away from the thing you're accumulating. As you're up here, you're adding to the thing you're accumulating. Okay? Go ahead.
You said that variable does not live outside of its integral. Is it because you're restricting its domain between A and B? Is that the same thing?
No. What I'm saying is, okay. This guy means nothing out here. You wouldn't talk about this x out here, okay? So this x is just involved in calculating this thing. In the same way that when you do this I means nothing outside. This I is just involved in telling you what to calculate in here. Once you've calculated it, no one cares anymore. Does that make any sense? So it has nothing to do with restricting the domain or anything. It has to do with when you write that symbol, the I is just inside that symbol. Outside it means nothing. Does that make any sense? So when I talk about this, I would never write, let's say, I would never write I times this. That wouldn't mean anything, okay? I is just in here. No?
Okay, so you solve for it using that, but you just didn't. Oh, because I'm confused because you're using the limit, your upper limit and your lower limit in order to calculate it.
Yeah.
But then, I understand that you can't move it outside of its function.
Yep.
But you still need to solve it using the limit, so is it not restricted by the limit?
Yes, you use these to calculate this thing.
Yes.
But that's not the same thing as what I'm talking about. What I'm talking about is that once you've calculated this thing, this x doesn't mean anything anymore.
Okay.
Okay, this x is just used to talk about what's going on in here and to talk about these guys, but outside, that's it. You get an answer, you get a number, it doesn't matter what you call that variable. Outside, you just get the answer. Does that make sense? So that variable doesn't show up anymore. Okay. All right. All right, let's do two of these examples. Example, evaluate the integral from -1 to 1 of x squared with respect to x. Okay, what are we looking for? We're looking for the signed area from here to here. Okay, we got this area last time. It was 1/3. What's this area? 1/3. Okay, so the whole signed area, again, signed area in this case is the same as area because we're always upstairs. The signed area is just 2/3. That's it. Okay, so you could write it like this if you wanted. Okay, so the area from here to here is the same as twice this area because x squared is even. And there you go, you get your answer that way. Okay? Symmetries are helpful. That's the lesson there. Another example. Evaluates. Incidentally, if this was x cubed and we were going on, let's say, -1 to 1, we'd get something like this. That negative contribution would exactly cancel the positive contribution. So if this was x cubed, your answer would be 0. Okay? All right, evaluate this thing from 0 to 2 pi cos x with respect to x. Okay. What do I look like? Okay, and I want the signed area. Okay. Those guys make a positive contribution, that guy makes a negative contribution. Ignoring the horrible scaling of this, what should the answer be? What do we guess when we don't know?
0.
Good. It's a great teaching method there. Okay, goose egg. the size of that area is exactly the same as the size of that area. Okay, the positive contribution exactly balances the negative contribution. When that happens, you just get an integral equal to 0. Okay, the signed area is equal to 0. So again, that's because of symmetries that we were able to notice this. Okay? So look for symmetries, see where areas are exactly equal, where they double in that case, okay, where they contribute in the same direction, or where they cancel, as in this case. Okay? Notice symmetries. Good? Okay. So the properties of this thing. Properties of the definite integral. Okay, if anything's weird, tell me. Okay, if you integrate from A to A, so from the same number to the same number, what do we get? Yes, the universal guess. Okay, why? Okay, the pictures I'm going to draw are not true in general, okay? They're just illustrations to show you what kind of thing is going on. Okay. What does this tell us? It tells us the area under the curve, the signed area under the curve, from A to A again. Well, if I'm going from A to A, this thing has no width, there's no area, so 0. Okay? No width, no area. Good? No width, no area. Signed or unsigned. 2. The integral from A to B of a constant C. So if you're integrating a constant function, it's C times B minus A. Incidentally, for each of these you can, not for each of these, for some of these you can spot an analog in the sum rules we talked about. So we talked about the properties of sigma notation. Some of these are similar to those. Okay? If you have questions about that, let me know. Okay? For any constant C. Constant meaning what? It means it has nothing to do with the variable of integration. Okay, you remember when we talked about sums, I said a constant was something that had nothing to do with the index. Okay, so sometimes I was pulling n's out of the sum. The reason is that n had nothing to do with I. Okay, so a constant is something that in this case has nothing to do with x. Okay, so it's not a function of x or anything like that. Okay, what am I doing here? Okay, we're going from A to B. We're talking about a constant function, and we want the area underneath. Hey, look, it's a rectangle. Okay, the base is B minus A, the height is C, the area is B minus A times C. It's as simple as that. Okay? Okay, this one's a bit weird. If I flip the limits of integration, the sign of the integral result flips. Okay? So for example, if I integrate x squared from 0 to 1, I get the signed area, 1/3. If I go from 1 to 0, then it's minus 1/3. Okay? Which is not the signed area. It's the negative of the signed area. So again, over here, what are we doing? Okay, let's say this. Okay, we're integrating this way. Okay, and over here, let's say we're integrating this way. Okay, I don't consider this one to be the most intuitive thing in the world. Just remember that when you're talking about areas or signed areas, you'd better be going from the smaller one to the higher one, okay? So something like 0 to 1. If you write 1 to 0, you're getting the negative of the signed area. Okay, so if you reverse the direction of integration, You reverse the sign of the integral result. Okay, two ways to think about this. You remember in the Riemann sum, we said the delta x, okay, the width of each subinterval was b minus a over n. Okay? So it'd be b minus a over n here, and in this case, your delta x would be a minus b over n. Easy. Okay? So in the Riemann sum, you go upper limit minus lower limit divided by n. Okay? If you swap the upper limit and the lower limit, that thing switches sign. Okay? So every term of the Riemann sum switches sign, so in the limit the integral switches sign, if you want to think of it that way. Or think about dx as a tiny change in x as the integrator, whatever that means. Goes through the interval. Okay, so as I go this way, okay, all my changes are positive. If I go this way, all my changes are negative. Okay, so I flip the sign. Okay, likely you won't be thinking about any of this. You'll just see something and you'll flip it if you have to, and then you'll remember to put a minus sign in front. That's really what you have to do. Okay. Again, all the explanations are to give you some sense of what's going on. Don't freak out. Once we got 4. Integral from a to b of c times f is equal to, guess what, c times the integral. Good. We see that all the time? We see it here too. For any constant c. So for any constant c, you can pull the constant out and then figure out the integral. Okay, and the constant again being something that has nothing to do with the variable of integration. You want to think about what we're doing there? Okay, supposing about this. Okay, so if that's f, then minus f will look like this. Okay? The signed area went from this positive thing to the same thing but negative. Okay? So as we scale the function, or sorry, as we flip the function vertically, we flip the signed area. Okay? Also, as we scale the function, so if that's f, let's say that's, oh boy. That's f, let's say that's 2f. Okay? As we scale the function, we also scale the area. Okay? Does that make sense? Okay? So vertical flips or scalings of the function result in exactly the same result in the area, or the signed area. We'll stop there. I'll finish the other two properties next time. We'll do an example, and then we'll move on. Any questions, come talk to me. Again, office hours today. Thank you, everybody. Okay, we're going to wrap up 5.4. We talked about the definite integral. We said what it was in terms of the Riemann sum. We talked about the bits of it. We talked about what signed area was. We talked about dummy variables. And we talked about some properties. And we evaluated some integrals based on symmetry. Okay, so we talked about properties. We did properties 1, 2, 3, and 4. My picture of 4 was crap. in technical language, so I'm going to do it again. So I said something like this before. If you have this, don't worry about it. Okay, for any constant c, here's my better version of the same deal, based on a whisper from the front row, which I may have imagined. Okay, we got a function there. If I imagine scaling that thing vertically, I get something that looks like that. Say 2f minus f would look something like that. Okay, what I'm saying is that if you scale the function by a factor of 2, then the area underneath scales by a factor of 2. Okay? And if I flip the graph vertically, then the signed area inverts sign. Okay? And that's all that thing says. Okay? Scale the function, you scale the integral, flip the function, you flip the integral. That's all good? Okay. Okay, and in practice you won't even be picturing that, but picturing it might be nice. Okay, a new one. Property 5. A lot of these will look familiar. If you integrate f at x plus g at x, that's the same as integrating f at x and adding the integral of g at x. Okay. Picture time. Okay, A to B. Suppose f looks like that. And again, all this is to give you some kind of a feel for what's going on in y, but in practice you often won't be picturing things. Okay, so suppose f looks something like that, g looks something like that. Okay, adding these things means that at every x value you add the heights. Okay, so what do you wind up with? Okay, so that's what that'll look like. So that's f plus g. At every x value, add this height to this height, and you get the height of f plus g. Yep, just add the value. Good, and it should seem reasonable to you that you get this area, based on that height thing, or just by looking at it, that you get this area, the area under this curve, by adding the areas under these two curves. Okay? So again, the height's added each x value, so the area is added. And guess what? This guy and this guy are those familiar properties that make something a linear operator. Life's good, you can bring out constants, you can break up sums and differences. Like so many of the other things we've seen. Final property. Okay, if you have a third point, C, okay, you integrate from A to C, and you integrate from C to B. And you add those two, you get the integral from A to B. Okay? Yes, ma'am.
So is number 5 good for subtraction as well?
Yeah, thanks to this thing, essentially. Yeah? Yeah, so if you imagine a negative c or just c being minus 1, you put them together, you get subtraction. That's right. Okay, good. Yeah, so if you feel like writing this as plus minus, that's cool. Okay, so what does this thing say? And by the way, all this stuff, these things are special pictures, right? These work for signed areas, they work for all sorts of cases, okay? These are just pictures to tell you what kind of thing is going on. Okay, so, how do we picture this? Okay, if you want this whole area, or signed area, you just add that signed area to that signed area. That's all that is, right? From A to C is this guy, from C to B is this guy, add them together, and you've got the overall. Okay, easy peasy. So this one essentially you're either merging or splitting vertically, this one you're merging or splitting horizontally. Okay, and everything on the board now is similar-ish to some properties that we saw, the sigma notation properties we saw. And again, I've only drawn special cases, these work more generally. Okay, any questions about any of that? UT. Okay. I'm probably going to have to tell you this at some point, so I'll tell you now. Do not do this. Do not. This will look familiar from the sum stuff. Okay, if you've got something like this, okay, don't do this. Okay, you can't do that. You're allowed to pull out constants. You're not allowed to pull out functions of the variable of integration. That's crazy. Okay. Also, don't do this. Okay. The integral of a product is not the product of the integrals. Okay, so there you go. Don't do those things. Use the rules that actually exist. Okay. Again, not. Example. Okay, so usually the point of a definite integral is that we want an area and we use the integral to get the area. Okay. We don't quite have the tools to do that easily yet, so now we're going to use an area to find an integral. So given this unnecessarily complicated looking function, 1/2 x plus 1, if x is between -1 and 0, square root of 1 minus x squared, if x is between 0 and 1, and minus x plus 1, if x is between 1 and 2. Okay. Compute the integral from, guess what, -1 to 2 of f of x dx. Okay, so what are you talking about? How do I do something like that? This is only here because it's doable. Okay, because we know what all those shapes look like and we know what the areas under them look like. So picture. Let's go there. -1, 0, 2, 1, minus 1. Okay, here, slope 1/2, y-intercept 1. Okay, so it's 1/2. Between 0 and 1, that thing is a bit of a circle. Okay, so it's a circular arc. Pretend that's a circle. Okay? We've seen things like this before. Okay, this is a circle with radius 1, centered at the origin, and it's the upper half of it restricted to that piece. So all you get is this piece of the circle. And finally, this guy, y-intercept 1, slope minus 1. Okay? All right. This subject always gets introduced with examples like this, where you can actually find the areas. Okay. Does that make sense? All right, we want the integral. What's the integral? The signed area. Okay, let's get the signed area. For the sake of using one of those properties, let's write it like this. Let's break it up. Break it up horizontally. Okay, break it up into natural pieces. Look after each one. Or just say, I need to calculate the signed area, and just calculate the signed area. So, if you know how to calculate the area of a trapezoid, that's what you do, okay? 1/2 plus 1 times 1 divided by 2. Okay, it's a trapezoid. So, look up that formula. Again, 1/2 times height times, let's say, average length. So 1 and 1/2. Okay, and that makes a positive contribution because you're upstairs. Okay, this guy, that's a quarter circle. The circle has radius 1. Okay, pi r squared divided by 4. Pi r, which is 1, squared divided by 4. Again, because it is a quarter of a circle with radius 1. Okay. Again, positive contribution there because we were upstairs. Now we're downstairs and we want signed area, so we better subtract this area. Okay, it's a triangle. Triangles are easy. Half base times height, so half of 1 times 1. Minus, because we're downstairs, a half of 1 times 1. And that's it. Okay, this is 3/2, so this whole thing is 3/4. 3/4 minus a half is 1/4. 1/4 plus pi quarters. 1/4 plus pi over 4. Okay, questions? Okay. If you don't know how to get the area of a trapezoid, you can break this up vertically into a rectangle and a triangle and add those up, and that works. And note, I said we get the signed area. Check that this is actually less than this. We're going from -1 to 2. We're going in the right direction. If we were going in the wrong direction, it'd be minus that. Okay? Yes, sir.
Is there a way to figure this out without drawing?
If you can recognize the shapes, yeah?
No, like,
If you want like some, yeah, yes. Not yet, but yes. Yeah, yeah, yes, but not yet.
okay.
Unless you know how to do the Riemann sums and limits and stuff for that, which might be fun. Well, you might be there for days. Okay? All right, the question I could have asked was, I could have said this is a velocity time graph, find the net displacement, exactly the same thing, okay? You're getting the signed area under the curve. Okay, if I said this is flow rate versus time, I could have said, give me the total accumulated volume, same kind of question. Any questions? And we move on. Okay, I'm gonna forget this if I don't say this now. For the previous lecture, we didn't do too much with the properties, okay? So I put up a PDF involving two of the integrals we already evaluated. So given those two integrals we already evaluated, move stuff around, flip things around, glue things together, and find some other integrals. All right, so look under my name on Learn. There's a PDF, another extra exercise. That's there now, and I'll put the solutions up tonight, okay? If you got any questions, let me know. Okay, so it's just playing with the properties of the definite integral.